Hello everybody. I'm going to be looking at chapters 9, 10, and 11 today, so we can look at those, make sure that you feel pretty good on them. You'll see my work here is kind of messy, but we'll go through it together so we make sure you understand. And as always, if you need more help or you have any questions, just call, text, email, get a hold of me, and we'll make sure that you're in good shape. All right, so let's look at chapter 9. So the first one that we've got a big set of data, and we actually have 3 different variables. We've got father's height, mother's height, and son's height. And the first question that they ask is, are the 3 samples independent or dependent? And these are dependent. They're dependent because a father's or a son's height, there's some sort of a relationship between how tall the kid is and how tall the parents are. Right, so it makes sense to keep these as grouped data. We're going to be looking at these in terms of a paired t-test and stuff later on. So we're going to be looking at the difference between the heights because we do have dependent variables. The next part, find the mean, median, range, standard deviation, and I skip variance. Remember, we always skip variance because we aren't really concerned with that, of the heights of the sons. So I had to look at this bottom row. This bottom row gives me all of the sun's heights, and then let me scoot it down. And so I ended up with my mean is 69.7, the median is 71, the range is 77, and then the standard deviation is 2.6. I have you skip C. We don't really concern ourselves too much with level of measurement. And then are the original unrounded heights discrete or continuous? And they are continuous. If they're unrounded, they're the original numbers, you're dealing with a measurement, and measurements are continuous. All right, so the next part asks you to construct a scatter plot, and you can do that. It wants you to do the, father and son's heights. So the father's height is the X, and then the son's height is the Y. And so your graph looks like that. There doesn't really appear to be any kind of a correlation. I could draw a line through there, but it doesn't really necessarily look like there's any kind of a strong correlation there. The next one, they want us to do a confidence interval for the mean son's height. So that's going to be T interval, and for me, my son's height, I had that in list 2. So I ended up using list 2 for that, and I've got 67.564 is my lower, and then the upper is 71.862. So we're 95% confident that the mean sun height is between 67.6 and 71.9 inches. All right, so for number 4, we're still dealing with that same situation. We haven't looked at anything else. So for this one, they want us to look at the difference between, a hypothesis test. Use a 0.05 significance level to test the claim that the differences between the fathers and their sons in their height have a mean of 0. And so this one is, remember, we'll put one of them into list 1, the other into list 2. And then list 3 is the list that we're going to be concerned with. So in list 3, we create this list of list 1 minus list 2. So, here. Oh gosh, I didn't even get my calculator out. Hold on. Silly me. And I don't think I saved my data in there either, so let me look at that real quick. Stat edit. No, of course I did not. Clear. Clear. Okay. I'll enter my data real quick. So the father and sons, right? You know, the good part about these videos is when I'm doing obnoxious stuff like this because I wasn't prepared, in class you had to just sit here. But now, you can fast forward. So all I'm doing is adding one of them into list 1 and then the son's heights, 71, 64, 71, 68, 70, 71, 71.7, and then 71. Okay, and then remember list 3, this is going to be my differences. So this one here, I go up here, and so I have list 3 is equal to, and then I say list 1 minus list 2. Okay, and so then I've got my data, and I can just do my t-test now on, and I can say I want it to use data. The mean difference for my hypothesis is going to be 0, and I want to use list 3. And this is the information that I come up with. Notice it matches what I've got here, right? My t-score is a negative 1.7. My p-value is 0.1326. That is a high p-value. It's higher than what my alpha was. So if my p-value is greater than alpha, we fail to reject our null hypothesis. These are the ones that you guys struggle with, right? So we are failing to reject. So we don't have evidence that the mean difference between father and son's height is not 0. Remember, it's that double negative that tends to kind of trip you guys up. The next one, they give you that normal quantile plot. And they say, okay, look at this one. Does that look like it's approximately normal? And it does look. It's reasonable to assume that that would be approximately normal. Okay, the next one, we've got breaking reaction times, and that's breaking reaction times between male and female. So we've got a big set of data. I'm not going to enter this in there again, but you could construct a histogram. If you just constructed one that your calculator gave you, that's fine. This is what theirs looks like. So if you just entered the data for, I want you to do it for male for the first one, and you can just enter your data in there and then tell it to make a histogram and then copy it down, that's fine. This one gives you specific class widths and a class starting point, and so you could easily create your frequency table, make your tally marks, and then turn it into a histogram. That's what I did to make mine match theirs. The next one, for number 7, you've got another normal quantile plot. This one is for breaking reaction times of females. And this does look to be like it's probably a normal distribution. It's very linear shaped. It doesn't have any definitive, like the one that we looked at in one of the previous videos, how it went up and then, kind of leveled out, right? It didn't have that logarithmic shape to it. This one, it's kind of just randomly scattered along that line, right? And then number 8, use the same data from exercise 6 and the same scale to construct 2 different box plots. And so for me, I just did that on my calculator. I just entered my data. I deleted it. Actually, did I? Oh, maybe I didn't. Hold on. I think I did, though. No, I didn't. Yay. See? So if I go to where my data is, I've got it in list 4 and list 5. I didn't delete that because that took forever to put in there. And so then I went to stat plot, and notice I've got 2 different plots on. I've got my males data is in list 4, and I'm telling it to make a box plot, and then I did the same thing with list 5, and those plots are both on, right? So when I go zoom 9, I can see both of them at the same time. So if I'm looking at these box plots, they overlap. So we don't necessarily have evidence that one is for sure greater than the other. If I had one box plot here and then the other one over here, right, where my endpoints don't overlap, then I could definitively say, this one is greater than that one. However, when we do look at it, it does appear that most men, so 75% of the data for males, is below half of what the women's is, right? It does appear that men tend to have a quicker breaking time based on this data, but we can't really say definitively unless we do a test, which is number 9. So number 9, we've got a 2-sample t-test, and so I'm checking to see if my 2 means are equal is my null hypothesis, and then they want us to just see if they're different, so that means that my alternative is a not equal. My alpha is 0.01, and so this, my data is in list 4 and list 5, remember? So I can go stat, over to tests, and remember, you've got that list we made a long time ago of all of the different types of tests that we've got. This one is a 2-sample t-test. And so I just used my data, told it to use list 4 and list 5. I've got not equal to, and everything else is the same. And so just calculate it. So it gives me my t-score and my p-value. My p-value is super tiny. It's definitely less than 0.01. So I can look at it and say that my p-value is less than alpha, reject my null, accept my alternative. We have evidence that the mean break time for men is different than for women. Okay. Number 10 wants us to look at some confidence interval stuff. So these ones, they first want us to look at the confidence interval for men's break time and women's break time. And so for men, it's in between 40 and 48.7 seconds long for those break times. For women, it's between 47 and 61, right? So they do overlap, so we don't have evidence just using these two to say that one is better than the other. However, it makes more sense to look at the difference between our two means and look to see if that difference could possibly be always positive or always negative, right? So this one right here is looking at the difference between the mean breaking time. So instead of just having just one mean in between those two things, we've actually got the difference between my two means. So 0 is not inside of this interval because, so that means that they are definitely going to be different. It means that my first one is less than my second one. It's always negative. So if I'm looking, if I'm looking at the difference between my means and it's always going to be a negative number, that means that my second number is always bigger. So that means that my mean break time for women is going to be higher than the mean break time for men. Okay? So that is chapter 9. Yay! Let's move on to chapter 10. All right, so the first one, we've got stalks and sunspots. So honestly, when I did this, I didn't really actually read the question very well. I kind of just looked and saw, oh, here's some numbers. This is what it wants me to do. And I know that, some of you guys do that too, especially with something like this. And now that I've read it, I really doubt that there's some sort of a relationship between sunspots on the sun and the stock market. But hey, you never know. So looking at this, the first thing they want us to do is just data analysis. So for the first one, they want us to just look at the sunspot numbers and find the mean, the median, the range, and the standard deviation. Remember, skipping that variance. It's quantitative. It's something that we're counting, right? It's not categorical. We're not looking at the color of the sunspot or something like that. It is quantitative data. Number 2, use a 0.05 significance level to test for linear correlation between those two things. And so for this one, remember when we're testing for a linear correlation, we're looking at rho, right? That's RHO. It's not a P. It's rho is equal to 0 or rho is not equal to 0. Alpha is 0.05, so this is that Lin regression t-test. So we just put our data into two lists, and then we just do that Lin regression t-test, and it gives us everything we need. So my t-score is 2.62, which is actually pretty high, and our p-value is pretty small. So we have evidence that there is a linear correlation between those two things, but does that mean that we should buy stocks based on the number of sunspots that are on the sun? No. Remember that correlation, let me write this down. Correlation does not imply what? Causation. I swear, as the year goes on, these videos get crazier and crazier because I really miss you guys. And it's weird talking to myself. All right, number 4. So number 4, the mean sunspot number for the past 3 centuries is 49.7. Use a 0.05 significance level to test the claim that the 8 listed sunspot numbers are from a population with a mean equal to 49.7. So as you've noticed, especially with these cumulative reviews, they're kind of throwing everything at you. So this is a good practice for you to, especially 9, 10, and 11, to really decide, what are they asking me to do? What type of data do I have? What am I going to use, right? So for this one, use a 0.05 significance level to test the claim that we've got a mean of 49.7 sunspots, right? So here's my mean of 49.7, and my alternative is that it's not equal to, right? They didn't say greater than or less than, they just said test that it is, so our alternative is always that it isn't. We just have one set of data, that's it. Even though we have more that was given to us, we're only right now concerned with sunspots, so it's just a t-test. List 2, alpha is 0.05, my t is negative 1.24, my p-value is 0.2549, which is really high. So my p-value is greater than alpha, we fail to reject our null. So we don't have evidence that the mean sunspot number is not 49.7. Okay? Number 5 is making an interval for that, right? Construct a 95% confidence interval estimate of the mean sunspot number and then write a statement that interprets that. So it's just a t-interval. Our data's already in there. We just plug it in. It's nice and easy. We're 95% confident the mean sunspot number is between 9.6 and 62.2, right? It's going to be somewhere in between those two numbers. It's a pretty darn big confidence interval because we have a really small sample size. All right, the last one that I had you do for this section is number 6. That's not a mistake. I did it on purpose. Numbers 7 and 8 are problems that I don't want you to look at because they're using things that we kind of skipped over. So number 6, cell phones and driving. In the author's hometown of Madison, Connecticut, there were 2,733 police stops, and 7% of them were attributable to improper use of cell phones. So use a 0.05 significance level to test the claim that the sample is from a population with fewer than 10% of police stops are attributed to improper cell phone use. Right? So in this case, we've got, this is my sample size. I'm dealing with percentages, right? So that means I'm going to be dealing with proportions. And I've only got one set of data. I've got one population, so this is a one prop z-test. Okay? So my p-hat is 0.07. And so remember, when we're doing that in our calculator, it asks us for an x and an n. So I figured out what 7% of those are, and it's about 191. So I did a one prop z-test. This is what I entered. My p-naught is going to be 0.1, right? So I'm looking to see is p equal to 0.1 is my null, and then less than is my alternative. And alpha is 0.05. Z is a negative 5.25. And so that's a super tiny p-value. Remember, if you say my p-value is 7.7, you're going to be wrong, right? Because it's times 10 to the negative 8. So my p-value is less than alpha, reject and accept. We have evidence that fewer than 10% of stops are due to improper cell phone use. Okay, so that's chapter 10. One more and you guys are done with your review. All right. So did I actually turn the page already? Yes, I did. Okay. So the first one that we're going to be dealing with is weather-related deaths, which is kind of strange, but so exercise 5 involved weather-related U.S. deaths. Among 450 deaths included in the exercise, 320 are males. Use a 0.05 significance level to test the claim. Among those who die in weather-related deaths, the percentage of males is 50%. So do half of the people that die in weather-related events are half of them male. So this is just exactly like what we just did. This is a one prop z-test. It's the same thing, right? My p is 0.05. For my null hypothesis, my alternative is that it's not. It's not 1/2, or it is, right? And then my alpha is 0.05. And so I just use my numbers. I plug them in. It's a one prop z-test. This is my x. This is my n, right? So I end up with z is 5.18. So my p-value is once again super tiny. Sorry, that was off the page there. So my p-value is less than alpha. Reject my null, accept my alternative. We have evidence that the proportion of, sorry, hold on. I was looking at the wrong one. So back up here, we've got z is 8.96. And my p-value is, and that was times 10 to the something. I forgot what it was. I didn't write it down. I'll write it down here in a second. Do they have it there? No, they just said that it was effectively 0. So I'll change it before I upload these. So we reject our null and accept the alternative. We have evidence that the percentage of males is not 50% for the people that die in weather-related accidents. So the next one is on whether or not chocolate makes you happy. So there was a survey done to see whether chocolate makes women happy. And so the first question is, yeah, there's a problem with it because it was sponsored by a chocolate company. So it would make sense that if it's sponsored by a chocolate company that there is a possibility that bias could be introduced. Part B, They want us to know how many people. So it was 85% of that 1,708 people. So that is, and rounding up just to, be appropriate, I've got 1,452 people out of the 1,708 said that chocolate makes them happy. So for number 3, they want us to construct a 99% confidence interval to estimate the percentage of women who say chocolate makes them happier. So it's going to be between 83% and 87%. Right? It's just a 1 prop Z interval. I'm still dealing with proportions. Remember, anytime you see things like percents, you're dealing with proportions, and I just have 1 sample. That's it. I don't have 2 different samples that I'm dealing with, so I've got a 1 prop Z interval. And so we're 99% confident the percent of women who chocolate makes happier is between 83 and 87%. Okay? Number 4, use the results to test the claim that when asked, more than 80% of women say that chocolate makes them happier. So looking here, it's just a 1 prop Z test this time, right? I've got my proportion for my null hypothesis, P equals 0.8, and then P is greater than 0.8. My alpha is 0.05. My Z-score is 5.18 with a super tiny p-value, so I can reject my null, accept my alternative. We have evidence that the proportion of women that chocolate makes happier is more than 80%, which makes sense because if we look up at our confidence interval, it's between 83 and 87, so it does make sense that it would be higher than 80%. Number 5 is when we're dealing with that denomination idea. We looked at problems like this multiple times where, they gave everybody $1, but they gave some people a $1 bill, other people they gave quarters, and then offered, do you want to buy gum? And to see if there was a difference between whether or not they spent their money. And so this one you're dealing with in China instead of in America, just to see if there's a difference there as well. And so this is a chi-squared test, right? We're in chapter 11, so we are looking at goodness of fit. So this is a chi-squared test of independence. That's the plan. So we can enter this into a matrix and get our data out. I'm going to look at this real quick just so that we can double check it. So remember, we can go to matrix, and I'm going to go over to edit. This is a 2 by 2, and I can just enter my data. So 60, 68, 15, and then 7, and then stat over to tests, and then, I should have gone up because that would have been quicker, but it's just a chi-squared test. And then just calculate it for me. So I've got my data right there. My null hypothesis, remember you can look in your notes for this, but the denomination and whether they spent the money are independent, right? The 2 variables are independent, and the alternative is they aren't independent. Remember, it's not that they're dependent, it's that they're not independent. Alpha is 0.05, my chi-squared test statistic is 3.409, and I end up with a not high p-value, but higher than my significance level, right? So I fail to reject. We don't have evidence that the denomination and spending the money are not independent. Okay. Number 7 is car crash costs, and that one we've got another set of data that we would enter both list 1 and list 2, and we would see, can I do a test of significance for it? I want to see, is there a linear correlation between how much it costs to fix the car and the type of crash injury, or type of crash, whether it was front or rear collision. My null hypothesis, rho, is 0. The alternative, it's not, which means that there's some sort of a correlation. Alpha is 0.05. My t-score is a negative 0.6587. My p-value is over 50%. That's a really high probability that this is just random, right? So we don't have evidence that there's a linear correlation between repair costs and front and rear crashes, okay? And then the last one is a normal distribution problem, okay? So we're looking at designing cars and aircraft. We must consider the forward grip reach of women. Women have normally distributed forward grip reaches, so that's how far forward you have to reach, right? And with a mean of 686 and a standard deviation of 34. So the car dashboard is positioned so that it can be reached by 95% of women. And what is the shortest forward grip reach that can reach it? So remember, it's kind of counterintuitive because 95% of women can reach it. So if you have a longer grip, then you can reach it. If your arms are too short, then you can't. So 5% can't reach it. So I've got inverse norm of 5%, and then, so 0.05 is my area. I've got my mean and standard deviation. So 630 millimeters or less is gonna be your cutoff point. The next one is if a car dashboard is positioned so that it can be reached by women with a grip reach greater than 650 millimeters, what percentage of women cannot reach the dashboard? Is that percentage too high? Okay, so the people that could not reach it is going to be that area to the left, and it ends up being about 14.5%. That's pretty high. If you've only got 85% of women that can reach the dashboard, that's a problem, right? Your car is made for bigger people. I like to be able to reach the dashboard. The next one says, find the probability that 16 randomly selected women have forward grip reaches, grip reaches. Let me start over. Find the probability that 16 randomly selected women have forward grip reaches with a mean greater than 680. Does this result have any effect on the design? So we've got to use the CLT, right? Central limit theorem, we have a sample and we're looking at that sample mean, right? So that changes our standard deviation. And so I've got 34 divided by the square root of my sample size. So my standard deviation is now 8.5, right? And so I'm looking for the area that's going to be greater than 680. So I'm using the same thing except for my standard deviation is now 8.5. And so that's about 76%. And then the next question says, does this result have any effect on the design? No. We don't care about a sample mean when it comes to the number or to grip reaches, right? We need every individual to be able to reach something, okay? All right, so that's chapter 11. We are done. Hopefully we can get these all in, and remember we've got a catch-up week next week. I will be entering these. I probably won't even be grading them until next week, so you've got plenty of time to get caught up. If you're behind, I'm not going to be entering stuff for you guys because you guys are in better shape than my other classes. So I miss you, and I hope everybody's doing good. Let me know if you need any more help, and I will hopefully see you around maybe. All right, have a good day.